Researchers found 21 zero-day vulnerabilities in FFmpeg. They used AI to do it, but they didn't use Mythos. Now, FFmpeg, if you're not aware, is one of the most widely used pieces of software on the internet. Literally, there are graphics and memes that are mostly true that show that FFmpeg basically holds up the entirety of the internet. FFmpeg is literally a multimedia library that allows you to convert one file format to another, to play media, to stream media, a bunch of stuff. This meme here implies that FFmpeg holds up things like YouTube, TikTok, Twitch, Instagram. This meme also implies that like Pornhub holds up the entirety of the rest of the internet. Not sure how that works, but in any case, FFmpeg, very, very important. I want to use this video to talk about not only the bugs that it found and kind of how they did it, but what AI means for the future of vulnerability research and why you may not necessarily need Mythos or $20,000 to find bugs like this. Now, FFmpeg is a code base written almost entirely in C with some inline assembly sprinkled in there for performance optimization. The code base written in C is a good thing inherently. FFmpeg is extremely performant and very good at what they do, but like any C code base, if it gets big enough with enough people, it is going to have vulnerabilities. It's not a skill issue in my opinion, it's just a language that allows that kind of thing to happen. FFmpeg developers, by the way, are some of the most skilled in the world, notoriously some of the best code base in the world in FFmpeg. But again, any code base that is in C will eventually have bugs. It's kind of inevitable. And with the advancements of AI, every day it's more and more likely that your organization might get hacked. You gotta be prepared, and that's why today's video is sponsored by ThreatLocker. ThreatLocker is a zero-trust platform that allows your organization to stop hackers if they get in. With deny by default policies, your organization controls what happens when a compromise occurs. ThreatLocker's device dashboard allows you to have visibility of all the devices in your organization. When they join your organization, they go through an application control learning period where ThreatLocker learns exactly what is required for your device to run. After that control learning period is over, it will deny the rest by default, giving you confidence that untrusted applications aren't running. So that when Frank from engineering inevitably runs, definitely not malware.ps1, ThreatLocker blocks it before it even runs. And if they really need to run it, they can put a little message in here where your SOC can respond to it as soon as they see it. And with ThreatLocker's new zero trust network access, you can push network rules down to the device where every connection is intentional and required by the baseline that ThreatLocker collects. All traffic is blocked by default unless it matches your rules, where you get to control which users can connect, which devices are approved, and which resources are accessible. Guys, you know the rule. The best way to go help the channel out is to go interact with the sponsor, go give ThreatLocker a shot, and next time zero trust comes up at your company, why don't you mention ThreatLocker? Thank you for sponsoring the video, ThreatLocker. Let's get back to it. 21 vulnerabilities found in FFmpeg, and you'll notice that all of them have some kind of overflow, stack overflow, heap overflow, integer overflow, a very common thing that occurs in C code bases, especially in C code bases that have to parse user data. If you consider that any one of the fields in the BMP file format could be malicious, for example, files like the image height, the image width, the bits per pixel, the X pixels per meter, that's very hard to say, etc. All of them do some kind of math that point into another location of memory where the actual pixel data is stored. If any of these fields are malicious and not properly validated, it could lead to some kind of overflow or underflow in a calculation, leading to access to memory outside of the bounds of this image data array. Very simple use case. Now, luckily, some of these bugs have only been around since 2023, some new file formats or new implementations of those file formats, but one in particular is actually a stack-based buffer overflow that has been around since 2003 with the original SDT implementation. Not sure what that is. It sat latent for 23 years, and even so, platforms like Google's Big Sleep and their OSS Fuzz repos that are actively looking for through AI and open source fuzzing, through those efforts to find bugs in FFmpeg, still couldn't find it. The bug that the blog author pointed out, which is a really crazy bug, is a skipped frame marker to PC control. Basically, what you have to do here is run FFmpeg and simply ingest an RTSP stream, okay? Literally, if you watch Twitch or you watch YouTube streams, any kind of live content, typically what's going on in the background is some kind of player is just reading the contents out of an RTSP stream, and the RTSP stream pushes an RTP stream, which is a real-time protocol. Basically, it's a protocol used for pushing real-time data, video data or audio data. The bug is actually crazy simple. So when you receive a packet from an RTSP server, you get data that says what size the packet is, and then you also use that to track the current position in that packet you're processing. Think of it like a cursor when you're doing a for loop over an array. As the client-side software, the software in FFmpeg is parsing this OBU data, the data inside of the element that you received. Every time it processes a byte, it calls AV grow packet. So as it's reading data, it's putting that data into packet data and growing it, also moving the packet position, the cursor, further along in the packet. Unless, of course, we put in an AV1 OBU temporal delimiter. Again, I'm not an AV1 guy. I don't know the spec very well, but basically inside the spec, according to a document that I read, it says in the spec that if you get a temporal delimiter, you're supposed to simply drop the information. Just get rid of it, move on, not a big deal. And you see that here. They move on by moving the packet position by increasing packet position by the OBU size, removing the remaining amount of data by the OBU size, and incrementing the amount of OBUs they've processed. But one thing you notice they didn't do is they didn't call AV grow packet, meaning the packet position could move out past the bounds of packet data and then allowing the user later to write data to that position, because later on in the code, after calling AV grow packet in a separate OBU, they can put data at the data location controlled by the user. By doing this, the attacker can write data that they arbitrarily control at the end of a buffer, actually specifically 67 bytes past the end of the allocation, which is a heap overflow. Now, when you do heap overflows, you have to do some kind of heap grooming to put an object that matters or a struct that matters inside the buffer at that location. If you want to leak data, you have to put data there that you want to leak. You want to overwrite a function pointer, you have to put a function pointer there. If you want code control, an easy way is to put a function pointer inside of the heap at that location so you can overflow it and overwrite that structure. And bada bing, bada boom, inside the AV buffer structure is a pointer of data, a pointer of size, good for arbitrary reads and writes, but more importantly, a function pointer that tells you how to free the AV buffer data. So if they groom the heap in the right way, they can create an AV buffer structure in the heap, overflow into that AV buffer structure, and then use that to get control of a function pointer and ultimately code control. Now, obviously, a lot more has to happen to bypass mitigations like ASLR, pointer authentication, a variety of other things, but this basic primitive is kind of how exploits have worked for the last 30 years. And just in honor of POC or GTFO, the author here shows in a stack trace that they set RIP to hex deadbeef, showing they have arbitrary code control, or at least the primitive for code control inside of FFmpeg via this bug, which is really nuts. I'm not sure how either Fuzzing or AI haven't found this bug to begin with. Literally, this is like if you send a certain kind of packet, the packet will get big enough and the packet will allow you to write outside of the bounds of another packet. By using AI to identify invariants, which is actually exactly what the researcher calls out, right? You look at this kind of packet and you should see pretty clearly it's the only packet that doesn't grow the packet via AV grow packet. And then also through like simple fuzzing, right? Using like ASAN and a variety of other fuzzers like OSS fuzz does. You know, if you run this and then run another packet after it, this write operation will trigger an ASAN crash, right? It'll trigger a crash that shows you memory is being written outside of bounds. The issue here may be that like all the fuzzers like OSS fuzz and otherwise may not be targeting the RTSP client in FFmpeg because it's kind of like a, I guess, trusted, if you will. You kind of trust the server you're connecting to when you're using RTSP, sort of. Either way, it's a really interesting attack surface. So again, there are 20 other 0 days. I'm not going to go into all of them. They're all generally the same idea of an overflow of some variety happening in the code base. I want to highlight what kind of I think this means for vulnerability research and people that want to do bug hunting or do bug hunting in general. I want to highlight first of all that you don't need Mythos to find bugs like this, and also you don't need to spend $20,000. While I think that Mythos may have some kind of special sauce in it that Anthropic has with other companies, there may be value in using a model that is more tuned to doing multiple bug chaining for like exploit development or like really, really heavy offensive security research. There is a way to do this kind of research and not spend 20 Gs. Now, I've done vulnerability research with Opus 4.7 and Sonnet 4.7, I believe, for the 4.6 or 4.7, I forget which one. One of the earlier like not 4.8 models, and it is actually very good as well at finding vulnerabilities. The hard part when you're doing this stuff is figuring out like the right way to prompt it. And I want to caveat that because I think a lot of people get lost in like, oh, I got to use like the right verbiage in my prompt and like talk to the AI in the right way. And that's not really what I'm talking about. What I mean here more is figuring out how to scope the problem down in a way that the AI can meaningfully handle it, and then how to allow the AI, how to give it tools to prove that it has solved the problem, right? And this is the blog post by Cloudflare that goes over some of their like, not really findings, but like ideas that came out of their Glasswing experience. What they talked about at the end of this is their vulnerability discovery harness, which I really, really like. It's a good way of kind of describing the VR process using AI. And I know the word harness is like super overloaded and kind of like annoying, but this is like a good way to think about this. You need to, when you're doing AI-powered VR, scope down the problem in a way that is meaningful to the AI. You don't just dump a code base into AI and say, find me the 0 days, please. Because AI, as we all know, has a context problem, okay? If you give the AI too many things to do or too much stuff, it'll just get lost in it. What you probably want to do is something like this, where you give it recon on the code base, You give it a small function or single file of code and say, hey, are there any things that could go wrong inside of this code base? And if the answer is yes, scope outside of that code base afterwards, figure out if the bug is actually reachable, and then finally write some kind of wrapper around it like an ASAN harness or a fuzzer to see if you can actually trace into that bug. This is literally, by the way, the way that people have been doing like vulnerability research for years. It's just now we have not really a programmatic, but kind of like an automated-ish way of doing this at scale. It doesn't depend on like hard mathematical models that like SMT solvers need, like Z3 or Enger. You can use AI to kind of solve through all those problems in more of like a top level way. This may be like the main differentiator between like the Mythos, like Anthropic blog post and like people like this. Like when Anthropic came out with their Mythos write-up, basically they said it took them like $20,000 of AI spend to find a single DOS vulnerability in FreeBSD, whereas this guy spent $1,000 on a non-Mythos model and found 21 vulnerabilities. I think that I'm, again, assuming the main differentiator here is going to be the harness, the way that it's prompted, and not like, again, verbiage. I mean like the process of ingesting the code and the harnessing that went around to prove that the bugs were real. Because again, problem with AI still is you get a lot of false positives. Anyway, guys, that's it for now. Thanks for letting me yap for a little bit. I appreciate y'all. If you're new here, hit that sub button. I do appreciate it. I have a video on FFmpeg's previous bugs down here, and also a video on the future of cybersecurity as it applies to AI. If either of those interest you, go check them out. We'll see you there. Later, guys. Bye.